All right, Honors Chem, today we are going to start putting those oxidation and reduction equations to good use, and we are going to start learning about electrochemistry and how we use electrochemistry to take chemical equations and get those chemical equations to use the flow of electrons across different things, i.e. our lights, our phones, or whatever, to actually do work for us so that we can actually generate electricity and use that to power things. Okay? So electrochemistry is the study of redox processes by which chemical energy is transferred or converted into electrical energy and vice versa. Electrical chemical processes are useful in industrial and critically important for biological functioning. By and large, our bodies work with electrochemistry. Our cells fire with electrical impulses, our nerves, everything. Okay? So, we're going to start out by talking about voltaic cells. Okay? Voltaic cells, for you guys, the common term is batteries. Okay? Voltaic cells are also called galvanic cells. So there's three different ways that we can use the vocabulary to mean the same thing: voltaic cells, batteries, or galvanic cells. Okay? All of these are electrochemical cells. Electrochemical cells that convert chemical energy into electrical energy. Okay? By spontaneous redox reactions. Okay? So we're using spontaneous redox reactions to get those flow of electrons. And that flow of electrons, we can convert the chemical energy into electrical energy. Now, I just want to dive off really quickly into a little bit of a history lesson. The reason that they are called voltaic cells is after the Italian chemist named Alessandro Volta. That's where we get the whole idea of a volt from. It's named after Alessandro Volta. He had this wonderful idea of stacking zinc and copper plates together with rags or paper that were soaked in salt solution, salt water, and he could get an electrical charge going if he stacked enough of these plates together. Okay? And then we also have another Italian chemist. That's why it's called galvanic. It's after Luigi Galvani, who actually realized that he could also get electrical charges going with certain things. And he realized that we could get those electrical charges to make things move, i.e. muscles. He realized that if he got zapped by that electrical charge, it made his muscles contract. So he actually took frogs and put these electrical currents across the dead frog legs and could get the frog legs to contract and move. So both of the pioneers of electrochemistry were about the 1850s, 1840s in Italy. Alessandro Volta and Luigi Galvani. Okay? So, we have an illustration down here of voltaic cells consisting of zinc anode, and we'll talk about what an anode means really quickly in a minute, immersed in zinc 2 nitrate solution, and a copper cathode immersed in a solution of copper 2 sulfate. The cells are connected by a potassium chloride bridge, aqueous salt bridge. Okay, now I'm going to go and we're going to piece apart all of the things that are going on in this cell. Okay? So let's look at this. So we've got our zinc over here, and we've got our copper over here. If you notice, the electrons, these red lines are showing us which way the electrons are flowing. So the electrons are flowing from the zinc to the copper. So that means the zinc is losing electrons, right? So the zinc is becoming oxidized because it is losing electrons. And the copper is gaining electrons, so it is becoming reduced. Okay? Now we said that zinc was the anode. So at the anode, that is where the oxidation happens. So I have a mnemonic here. So we say an-ox. So the anode is where oxidation happens. Okay? That also, in terms of a battery, this is where we would consider that negative pole of the battery. So if you've ever pulled a battery out and you see that it has a negative end and a positive end, this would be considered the negative end of the battery. Okay? So copper, on the other hand, is gaining these electrons, so it is being reduced. And we said the copper was the cathode. So copper reduced is cathode. And my mnemonic for that is red reduced cat. So a red cat is the cathode, and that is where the electrons are going to. This is the positive end of the cell. So if you had a battery, this would be the positive end of that battery. Okay? So let's take a close look at what's going on inside this cell. So I have zinc losing, so one atom of zinc is going to lose 2 electrons. Okay, so when the zinc loses those 2 electrons, it's going to create a zinc plus 2 ion. And the zinc plus 2 ion is going to come off that zinc bar and dissolve into the solution. So by and large, this zinc bar is losing mass because it is dissolving into the solution. Okay? So as more and more of these electrons are being taken off the zinc bar, more and more of these zinc ions are going to be coming into solution. So I'm going to create a lot of zinc plus 2 ions in solution. Okay, so eventually that solution is going to become pretty positively charged. Okay, so if this solution becomes really positively charged, are these electrons going to want to leave it? No, they're going to be really attracted to those positively charged things. So we'll talk about what happens to keep that still flowing in a minute. I want to talk about the copper really quick. So as the electrons come over here from the zinc and come and flow over to the copper, notice the electrons flow down this copper, and I have copper plus 2 ions in this solution. And these electrons will bind with this copper plus 2 solution, or is it a plus 1? Plus 1 solution, or plus 2, and the copper will solidify onto this bar. So these copper plus 2 ions hook up with these electrons and they solidify onto this bar. So the copper is gaining mass. Okay? So that means that the negative ions in this solution that we balanced it out with, copper sulfate, we're going to have a lot more copper sulfate in that solution than copper plus 2 ions, because the copper plus 2 ions are going to solidify onto that bar. Okay, so we get a buildup of negatives here, and we get a buildup of positives over here as these electrons flow. So if we keep getting these buildups, are these electrons going to keep flowing? Are electrons going to want to leave a positively charged thing and go to a negatively charged thing? No. Opposites attract. So how do we keep it flowing? We keep this flowing by putting in a salt bridge. So this here is the salt bridge. So we have a salt that is packed into, and it's dissolved, and it's usually packed into some kind of a gel-like structure so the ions can flow. So this way, we can get the ions that are needed to equal out the charges to flow in the directions. So here, because we have a buildup of positives, the chlorides are going to flow this way to even out those charges. Okay, so that way the electrons can keep flowing, and here the potassiums are going to keep flowing this way to even out these charges so that the sulfate has equal charges going on. Okay, the other thing that this salt bridge allows us to do is, if you've ever taken physics, it allows us to complete the circuit. In order to have electricity flowing, we have to have a complete loop. So it allows us to complete the whole entire circuit. So we have one continuous loop that the electrons can flow and go through. Okay? So let's look and see what is happening at the anode. Remember, the anode is where oxidation happens, and we have zinc being dissolved. So our anode reaction is right here. We start with solid zinc, and as we have that zinc react, it goes to zinc plus 2, and we have 2 electrons being given off. Okay, so that is the anode reaction. Remember, anode is always where we are losing electrons. It's always the oxidized end of the reaction. Okay, the cathode reaction is the reduction reaction. Okay, so here's our reduction reaction. We have copper plus 2 coming from the solution, grabbing electrons that are coming from the zinc, and then that copper plus 2 deposits on that copper bar that is the cathode. So that copper bar is gaining mass. Okay? So when we have the overall reaction, we have to balance the electrons coming and going. And here our reaction is nice and easy because we have 2 electrons leaving zinc, and we have 2 electrons coming to join the copper. So the electrons coming and going in this are nice and already balanced. So if we added up these 2 reactions together, these electrons, by and large, are on the opposite sides of that reaction arrow. So we can really essentially cancel them out, can we not? Yeah, because they're on opposite sides. So we would have zinc plus copper plus 2 going to zinc plus 2 and copper solid. That would be our total reaction. That is what we would see. So we would have the zinc going to ions, so that zinc would lose mass. And we would have copper ions going to solid copper, so that copper would gain mass in that voltaic cell. Okay? So what is the substance oxidized? Remember, oxidized is losing electrons. So what lost electrons? That would be the zinc, right? Zinc is what is oxidized. Okay? What's the substance that gained electrons? What's reduced? What got reduced? Well, we started off with copper plus 2. So copper plus 2 is the stuff that was reduced. Okay, so the oxidizing agent, what helped zinc get oxidized? Well, it was the copper plus 2 because it accepted the electrons from the zinc. What was the reducing agent? What helped copper plus 2 get reduced? That was the zinc by giving it the electrons. Okay? And yes, I really should be putting states in here, but, not necessarily going to hold you over it. Okay? So we will look and see what the value of this cell will be. So in order to see how many volts we could get off of this cell, we're going to have to look at the standard potential. So here we go. We have this standard potential cell, and these are reduction potentials. And remember, the zinc got oxidized, so we're going to have to flip the reaction with the zinc. So let's take a look at zinc really quick. Let's see if we can find zinc in here. So we wanted zinc to go to zinc plus 2. We have zinc plus 2, but we're going to have the opposite. So if we have zinc going to zinc plus 2 and 2 electrons, isn't that electron potential then, instead of being negative 0.7618, it's going to be positive 0.7618 because it's going to be the opposite. Okay, so let's put that down here. So zinc plus 2 to 2 electrons. Zinc plus 2 electrons, so it's this direction, is going to be a negative 0.7. Let's get my, oops, that didn't switch fast enough. Negative 0.762. Okay, I'm just going to round to the hundredths. Okay, now notice for our copper, so actually let's not do our copper yet. Let's look at the reverse. So notice these are the reverse of each other. So the potential for the oxidation would be the opposite. It would be positive 0.762 volts because I'm doing the opposite direction. Okay, let's look for copper plus 2 on this. So if I find copper plus 2, do you guys see it on here? It's the very top. Actually, it's the second from the top. Okay, so copper plus 2 electrons. Copper plus 2 electrons. Positive 0.342. But if I do the reverse, I'm going to take the negative. Okay, do you see that? So if I want to oxidize something, I've got to take the reaction from the standard reduction table, and I've just got to flip that cell potential. Okay, the other thing I want to show you on this standard cell potential is where 0 is. Notice that our 0 value here on this potential table is hydrogen. Okay, so hydrogen is 0. For some reason, they chose hydrogen to be 0. It really is arbitrary. Any of these elements could be 0, but they used 0. So these standard potentials, these standard reduction potentials, are all based around hydrogen. Okay, it's all based on hydrogen. Hydrogen is our 0. Okay, and you'll notice that some of these are positive and some of them are negative. So lithium, for example, is a negative 3. Calcium is a negative 2.9 essentially. Sodium is 2.7. And then you'll notice we have all kinds of different values. We have just ions, and then we have water going to hydrogen and hydroxide. We're going to have, let's see, some of these we have lead 2 sulfate with sulfuric acid. So there's all kinds of different reactions that we're going to be doing. We have hydrogen peroxide here. So you need to be very careful with what you're looking up. Make sure it's the correct charge and make sure it's what you're dealing with, okay? Now, let's look at the cell potential. When we looked at that cell, we look at how we get the overall potential to be positive. So we need that cell potential to be positive, okay? So when we looked at our cell, we had zinc being oxidized, right? We used this. And we had copper +2 being reduced. We use these, okay? So when we do a cell potential, we add these two up. So just like we added the reactions together to get zinc plus copper +2 to give us zinc +2 plus copper solid, we're going to add these two potentials up. So if I add positive 0.342 plus positive 0.762, I get a voltage of 1.104 volts. 1.104 volts. Okay? In order for a voltage or a cell to be spontaneous, the voltage has to be positive. Okay? If our voltage is negative, that cell is not spontaneous. It will actually run the opposite way of what you have it. Okay? So notice we are adding and subtracting here. So when we do voltages, we are going to look for place value for our sig figs. Okay, so these all go to the thousandths, so I can use my answer out to the thousandths. So 1.104 will work. Okay, so let's see if there's anything else I want to say about this. So just remember, we need the salt bridge to give us the flow of ions so that we can keep the flow of electrons going over the wire. And the reason we want the flow of electrons, that flow of electrons provides electrons and the energy to do work, like light a light bulb, or maybe you turn on my calculator and use my calculator, or this computer that I'm using right now, my cell phone, my watch. We use batteries and we use electricity all the time, all day long. We're pretty dependent on it in this country. Okay? We're really, really dependent on it in this country, actually. All right. So let's do a couple more practice. Okay. So if I wanted to use, oops, let's get this off of here. Let's do some more practice with some cells here. So I have a cell where I have copper and I have hydrogen. We're using hydrogen in water, okay? So let's look at copper and the voltage on hydrogen and the voltage on copper. So Copper, we have going to copper plus 2. So we're still going to use this same equation. We have copper plus 2 electrons going to copper at being 0.342. So copper plus 2 electrons going to solid copper, giving us a voltage of 0.342 volts. Okay? The next thing we need to look at is hydrogen. So let's see if we can find hydrogen. Notice hydrogen is 0. Okay? So we have hydrogen plus 2 electrons. 2 hydrogens plus 2 electrons going to hydrogen gas, and that equaling 0 volts because that is our 0. So we both have these as being reduced, right? Something has to be oxidized. It's redox, right? So we have to figure out which one we can reverse while still have this being positive. So we always reverse the one that has the smaller value, okay? So which one is bigger, 0.342 or 0? 0.342. So we're going to keep that one. We are going to reverse this. So this one is the one we are going to flip or reverse. So this is going to become oxidized. So we are going to write this then as hydrogen going to hydrogen plus 2 electrons, and that will be 0 volts. Okay? So we're really not going to use that. So we're going to use these two equations together. And notice the electrons are on opposite sides, and there are 2 of them. So our overall reaction, we're going to have copper plus 2 plus hydrogen going to 2 hydrogens plus solid copper. Okay? So that would be our overall reaction. And when we add these 2 together, our voltage would be a positive 0.342 volts. Okay? So if we look at this diagram, is that what we see? Okay, we do indeed. So the electrons come from hydrogen. Okay, so the hydrogen is providing the electrons. So we have the hydrogen being given, making ions. So the electrons are flowing to the hydrogen, from the hydrogen to the copper. Those electrons are grabbing the copper plus 2 from the solution to become copper solid, and then it's depositing on the copper. So our copper is gaining mass, which we would see here. So this is gaining mass. Okay. And we have our electrons flowing this way. So if we keep on having electrons joining in here, this is going to become more and more negative here. And if the electrons keep leaving over here on the hydrogen, this is going to keep on becoming more and more positive. So if we have a salt in here, let's just put a really basic salt in here, sodium bromide. If I have more and more negative electrons coming in to the copper side, what do I need to balance that out? Yeah, I'm going to need to have sodiums coming in here to balance those charges out. And if I keep having electrons coming out of here and leaving me with hydrogens, I'm going to need the bromides to balance that side out. Okay? And we are going to take hydrogen gas and make hydrogen ions here. Okay? So you'll see in the cell potential, we took 1 and we took the reduced and we actually added the oxidized. So I don't like this in that it says the E naught of the reduced minus the oxidation, because the oxidation you should flip. So you're actually adding them together. Okay? So remember that the one that is oxidized needs to have a flipped value. Okay? I think they put the negative in there because a lot of people don't flip the value, but I always like to flip the values because it helps us balance the equation. Okay? So we want to calculate the cell potential for copper plus 2 going to solid copper and zinc plus 2. And we've already done this. So we're going to look at this value here. So copper plus 2 going to solid copper is a positive 3.342. Okay? So this is a positive 342 volts. And zinc solid to zinc plus 2. If we look on our cell potential table, zinc solid going to zinc plus 2, so it's going to be the reverse of this, is going to be a positive 0.762. Okay, so we're going to add these two together, and when we add those two together, we get a voltage of 1.104 volts. Okay, remember, we want a positive voltage to be spontaneous. Okay, so if you get a negative voltage, you know that you've added things wrong. It's not a spontaneous cell. Okay, so let's do another one. We want to calculate the cell potential for the following half reactions that represent these half cells. So we're going to look at iodine, 2 electrons going to 2 iodine, and we're going to look at iron plus 2. So we're going to look at the cells here. So let's look for iodine. So if I look for iodine, do you guys see it? I have a positive 0.5355 volts for iodine. Okay, so I'm going to write that. So I have a positive 0.5355 volts for this. Now I need to look for the iron plus 2. Make sure it's plus 2 that you're looking for. So on this, we're going to look for iron plus 2. Do you guys see it? It's right here. Oops. So iron plus 2. Okay, so iron plus 2 going to solid iron is a negative 0.447. Okay. Okay, this will give me a negative 0.447 volts. Okay, now if you realize these are both written as reductions, I need to have one of them be oxidized. So which one am I going to flip? Which one can I flip and still have an overall positive value? Yes, I am going to flip the iron. So I'm going to flip this. So the iron is actually going to become iron solid, going to iron plus 2 plus 2 electrons, and that's going to have a value of a positive 0.447 volts. Okay, So if I put these two together, I have a reduction and I have an oxidation. So I have a redox. I have a reduction and I have an oxidation, which is what I need. Okay. Now, do we have the same amount of electrons coming back and forth? Yes, we do. So if I put these two equations together, notice the electrons are on opposite sides of the equation, so they can essentially cancel. So my overall reaction here is going to be iodine, solid, plus iron, solid, going to iron plus 2, aqueous, plus 2 iodides, aqueous. Okay? So to find the voltage, I'm going to add these two together. So if I take 0.5355 plus 0.447, that gives me a voltage of 0.9825. Now notice this goes to the 10,000th and this goes to the thousandths. So I can really only go to the thousandths. So this 5 tells me to round up. So with sig figs, I would do 0.983 volts on that cell. Okay? So that is how we determine how electrons are flowing. That is how we determine what's coming and going, what's being oxidized, what's being reduced. So have a great day, and we will do some more practice next time. We'll see you later. Bye.